Hi and Assalamualaikum to everyone. Our group would like to present about experiment 6 high performance liquid chromatography HPLC for subject CHM260. We from A4AS 120513. So I would like to introduce our team members. The first one is Khalil Danish Irfan bin Hara Azam. The second one is Ahmad Zaki bin Ashran. The third one is Hazim bin Hawari. Next member is Farah Damia binti Zamri, Nur Safira binti Muhammad Khairi, and the last one is Nur Laila Maisarah binti Azman.
So for the introduction, this experiment related to chromatography. Chromatography is a technique to separate, identify, and measure components in a mixture. It's widely used in medicines, food analysis, and biotechnology due to its speed, accuracy, and efficiency. It's involved in two phases. The first the first phase is stationary phase and the second one is mobile phase. Components separate based on their interaction with these phases. Techniques like gas chromatography (GC) and high performance liquid chromatography (HPLC) are used for analyzing substances in various fields. For this experiment, they have three objectives. The first one is to determine the retention time of standard solution caffeine. The second one is to identify the caffeine peak in a soft drink sample. And the last one is to determine the amount of caffeine in soft drink sample using response factor method.
We begin by preparing the sample and standards. We first make a caffeine and standard solution and dilute the Levita and Coca-Cola samples if necessary to ensure they fit within the linear range of our HPLC system. To ensure accuracy, we filter all solutions through a 0.5 micrometer membrane to filter to remove any particulates. Next, we set up the HPLC instrument. We turn it on and let the system equilibrate with the mobile phase until the baseline stabilizes. For the separation, we use C18 reverse phase column, which ensures proper resolution. For the mobile phase, we prepare a mixture of water and acetonitrile. After mixing, we degas the mobile phase to remove any air bubbles that could interfere with the analysis. Once everything is prepared, we adjust the flow rate, typically 1.0 microliter per minute, and set the column to temperature to 30 degrees. We inject 10 microliter of each sample and standards using the auto sampler or manually, and start recording the chromatograms. Finally, we analyze the data by identifying the caffeine peaks. We match the retention times with the standard and quantify the caffeine concentration by comparing the peak areas with the standard's known concentration. This is how we ensure precise results in our caffeine analysis.
Hi, my name is Nur Safira and I'm going to talk about the diagram of HPLC system. An HPLC system is designed to separate, identify and quantify components in a mixture. It starts with solvent severe containing the mobile phase, which is pumped through the system by a high pressure pump to ensure a steady flow. The sample is introduced into the mobile phase stream via an injector, typically used an injection loop for precision. The mixture then enters the columns, the core of the system, where separation occurs based on the interaction of the sample components with the stationary phase and the mobile phase. As the separated components exit the column, they pass through the detector, which identifies and measures them, often using UVVs or mass spectrometry. Finally, the data system processes the signals from the detector, producing a chromatogram that represents the separated components and their quantities. The diagram shows the HPLC workflow, starting with the solvent reservoir holding the mobile phase, which is pumped through the system. The injector introduces the sample into the flow, directing it to the HPLC column where components are separated. The detector identifies and measures the separated components, sending data to the data acquisition system for analysis, while waste is collected.
Alright everyone, now I will explain the result for standard caffeine solution. First, as you can see, we got the retention time for standard caffeine solution is 2.482 minutes. Meanwhile, the peak area for standard caffeine solution is 6249.5 full at 779 milliabsorbent unit per second, which is 100% of the total area. This chromatogram represents the pure caffeine standard used as reference to identify and quantify caffeine in other sample.
Result in Coca-Cola. I will now explain based on the printed result and graph that have been shown in the slide. First, for Coca-Cola sample, the retention time RT for the caffeine peak at 2.481 minutes, which matches the standard. And then peak area for caffeine is 7001.12365 milliabsorbents unit seconds. This approximately at 57.355% of the total area. As you can see, the additional peaks represent other compounds present in Coca-Cola. Now, for the last result of the day, result in Levita. In Levita sample, the retention time RT for the caffeine peak at 2.479 minutes, which matches the standard. And then the peak area for caffeine is 5978.01367 milliabsorbents unit second, which is approximately 9.48% of the total area. And as you can see, the other peaks represent additional components in the Levita tree.
For the calculation, response factor equal to peak area caffeine standard divided by concentration of caffeine standard 6249.48779 divided by 0.1 times to 1000 ppm and get 62.4948. Next, response factor for unknown sample is equal to peak area caffeine in sample divided by response factor 7001.12345 divided by 62.4 and get 112.027 ppm. Concentration of caffeine in Coca-Cola. And last one is concentration of caffeine in Levita is 1.11511 times to 10 power 4 divided by 62.49488 and get 178.43 ppm.
Next, I'm going to talk about two key points in the discussion regarding caffeine analysis using Hplc. First, the retention time consistency shows that caffeine peaks in all samples consistently appear at around 2.482 minutes. This uniformity confirms the proper identification of caffeine and demonstrates the reproducibility and reliability of the Hplc method. Second, the quantification of caffeine indicates that the peak area for caffeine in Coca-Cola is 7001.12365 milliabsorbent units is larger than that in Levita, which is 5978.01367 milliabsorbent units, suggesting that Coca-Cola contains more caffeine. The caffeine concentration in a sample can be calculated using this formula. Caffeine concentrations in sample is equal to peak area of sample divided by peak area of standard times with concentration of standard.
Observing the chromatograms, we see sharp, well-defined peaks that highlight the efficiency of our Hplc system in separating caffeine from other components. This level of precision is achieved through the careful selection of the column and optimization of the mobile phase. These factors work together to ensure reliable and accurate separation, allowing us to confidently analyze the caffeine content in our samples. In our analysis of Levita and Coca-Cola, additionally, peaks were observed in the chromatograms. This likely represent other ingredients such as sugars, flavoring, or preservative. The important takeaway is that these peaks do not overlap with the caffeine peak, demonstrating the specificity of our method. This ensures that our results for caffeine content are not affected by interference from other compounds in the sample. Analyzing the beverage composition reveals a significant difference in caffeine content. Coca-Cola has 57% of its total chromatographic area corresponding to caffeine, compared to 9% of Levita. This indicates that caffeine is a more prominent ingredient in Coca-Cola, while Levita contains higher concentration of other compounds. This finding highlights the distinct formulation of these two popular beverages. Our method has important application in the beverage industry. It can be used for quality control to ensure that caffeine level match labeling, claim and comply with regulatory standards. Additionally, it can detect adulteration during production, ensuring the integrity of the final product. By applying this analysis, we contribute to the production of safe, high-quality beverage that meet consumer expectations.
We already reached the conclusion for our presentation. In conclusion, high-performance liquid chromatography analysis show that the method is reliable and effective for the characterization and quantification of caffeine in complex metrics such as in the case for Levita and Coca-Cola. The retention time of caffeine was the same in both standard and sample analysis, proving that the method is accurate. As expected, Coca-Cola had a higher caffeine concentration than Levita based on the peak area comparison. The separation of caffeine from other components indicate the selectiveness and robustness of the high-performance liquid chromatography method. Besides, sharp reproducible peak further signify the reproducibility of the system. Thus, this is useful to analytical tool in routine quality control and multi-8 component analysis in beverage and various caffeine containing products.